Hello friends, during our previous discussion we talked about what synchronous and asynchronous counters are. We learned that a group of flip-flops is a counter. The number of flip-flops used and the way in which they are connected determines the number of states and also the specific sequence of states that the counter goes through during each complete cycle. In today's discussion, we shall be talking about the 4-bit synchronous binary counter, synchronous decade counter and the up down synchronous counter, and finally, the design of synchronous counters. 4-bit synchronous binary counter. Figure shows a 4-bit synchronous binary counter and its timing diagram. This particular counter is implemented with negative edge triggered flip-flops. The reasoning behind the J and K input control for the first 3 flip-flops is the same as previously discussed for the 3-bit counter. The 4th state, flip-flop 3, changes only twice in the sequence. Notice that both of these transitions occur following the times that Q0, Q1 and Q2 are all high. This condition is decoded by AND gate G2, so that when a clock pulse occurs, flip-flop 3 will change state. For all other times, the J3 and K3 inputs of flip-flop 3 are low and it is a no change condition. A 4-bit synchronous decade counter. A BCD decade counter exhibits a truncated binary sequence and goes from 0000 through the 1001 state rather than going from the 1001 state to the 1010 state. It recycles to the 0000 state. A synchronous BCD decade counter is shown in figure. The timing diagram for the decade counter is also shown. You can understand the counter operation by examining the sequence of states shown in this table. First, notice in the timing diagram of decade counter that flip-flop 0 toggles on each clock pulse. So, the logic equation for its J0 and K0 inputs is J0 is equal to K0 and is equal to 1. This equation is implemented by connecting J0 and K0 to a constant high level. Next, notice in table that flip-flop 1 or Q1 changes on the next clock pulse each time Q1 is equal to 1 and Q3 is equal to 0. So, the logic equation for the J1 and K1 inputs is J1 is equal to K1 and is equal to Q0 into Q3 bar. This equation is implemented by ANDing Q0 and Q3 and connecting the gate output to the J1 and K1 inputs of flip-flop 1. Flip-flop 2 or Q2 changes on the next clock pulse each time both Q0 is equal to 1 and Q1 is equal to 1. This requires an input logic equation as follows: J2 is equal to K2 and is equal to Q0 into Q1. This equation is implemented by ANDing Q0 and Q1 and connecting the gate output to the J2 and K2 inputs of flip flop 2. Finally, flip flop 3 or Q3 changes to the opposite state on the next clock pulse each time Q0 is equal to 1, Q1 is equal to 1 and Q2 is equal to 1, that is state 7, or when Q0 is equal to 1 and Q3 is equal to 1, that is state 9. The equation for this is as follows: J3 is equal to K3 and is equal to Q0 into Q1 into Q2 plus Q0 into Q3. Up-down synchronous counters. An up-down counter is the one that is capable of progressing in either direction through a certain sequence. An up-down counter, sometimes called a bidirectional counter, can have any specified sequence of states. A 3-bit binary counter that advances upward through its sequence, that is 0, 1, 2, 3, 4, 5, 6, 7, and then can be reversed so that it goes through the sequence in the opposite direction, that is 7, 6, 5, 4, 3, 2, 1, 0, is an illustration of up-down sequential operation. In general, most up-down counters can be reversed at any point in their sequence. For instance, the 3-bit binary counter can be made to go through the following sequence. Till 5, the counter is an up counter, and then it is reversed to down for 3 digits. Again, it is an up counter for 5 digits, and so on. Table shows the complete up-down sequence for a 3-bit binary counter. The arrows indicate the state-to-state movement of the counter for both its up and its down modes of operation. An examination of Q0 for both the up and down sequences shows the flip-flop 0 toggles on each clock pulse. Thus, the J0 and K0 inputs of flip-flop 0 are J0 is equal to K0 and is equal to 1. For the up sequence, Q1 changes state on the next clock pulse when Q0 is equal to 1. For the down sequence, Q1 changes on the next clock pulse when Q0 is equal to 0. Thus, the J1 and K1 inputs of flip-flop 1 must equal 1 under the conditions expressed by the following equation. For the up sequence, Q2 changes state on the next clock pulse when Q0 is equal to Q1 and is equal to 1. For the down sequence, Q2 changes on the next clock pulse when Q0 is equal to Q1 and is equal to 0. Thus, the J2 and K2 inputs of flip-flop 2 must equal 1 under the conditions expressed by the following equation. Each of the conditions for the J and K inputs of each flip-flop produces a toggle at the appropriate point in the counter sequence. The figure here shows a basic implementation of a 3-bit up-down binary counter using the logic equations just developed for the J and K inputs of each flip-flop. Notice that the up down bar control input is high for up and low for down. the 74HC190 up-down decade counter. Figure shows a logic diagram for the 74HC190, an example of an integrated circuit up-down synchronous counter. The direction of the count is determined by the level of the up-down input. When this input is high, the counter counts down. When it is low, the counter counts up. Also, this device can be preset to any desired BCD digit as determined by the states of the data inputs when the load input is low. The maximum minimum output produces a high pulse when the terminal count 9 is reached in the up mode or when the terminal count 0 is reached in the down mode. This maximum minimum output along with the ripple clock output and count enable input is used when cascading counters. Design of synchronous counters. In this topic, you will see how sequential circuit design techniques can be applied significantly to counter design. In general, sequential circuits can be classified into two types. First are those in which the output or the outputs depend only on the present internal state, and second are those in which the output or the outputs depend on both the present state and the input or inputs. A general model of a sequential circuit. Before proceeding with the specific counter design technique, let us begin with a general definition of a sequential circuit or a state machine. A general sequential circuit consists of a combinational logic section and a memory section, that is flip-flops, as shown in this figure. In a clocked sequential circuit, there is a clock input to the memory section as indicated. The information stored in the memory section as well as the inputs to the combinational logic is required for proper operation of the circuit. At any given time, the memory is in a state called the present state and will advance to a next state on a clock pulse as determined by the conditions on the excitation lines. The present state of the memory is represented by the state variables. These state variables along with the inputs determine the system outputs. Not all sequential circuits have input and output variables as in the general model just discussed. However, all have excitation variables and state variables. Counters are a special case of clocked sequential circuits. In this topic, a general design procedure for sequential circuits is applied to synchronous counters in a series of steps. Step 1. State diagram. The first step in the design of a counter is to create a state diagram. A state diagram shows the progression of states through which the counter advances when it is clocked. As an example, figure is a state diagram for a basic 3-bit gray code counter. This particular circuit has no inputs other than the clock and no outputs other than the outputs taken off each flip-flop in the counter. Step 2. Next state table. Once the sequential circuit is defined by a state diagram, the second step is to derive a next state table which lists each state of the counter along with the corresponding next state. The next state is the state that the counter goes to from its present state upon application of a clock pulse. The next state table is derived from the state diagram and is shown in table for the 3-bit gray code counter. Q0 is the least significant bit. Step 3. Flip-flop transition table. Table shown here is a transition table for the JK flip-flop. All possible transitions are listed by showing the Q output of the flip-flop going from present states to next states. Qn is the present state of the flip-flop before a clock pulse, and Qn plus 1 is the next state after a clock pulse. For each output transition, the J and K inputs that will cause the transition to occur are listed. An X indicates a don't care. The input can be either a 1 or a 0. To design the counter, the transition table is applied to each of the flip-flops in the counter based on the next state table. Step 4. Carnot maps. Carnot maps can be used to determine the logic required for the J and K inputs of each flip-flop in the counter. There is a Carnot map for the J input and a Carnot map for the K input of each flip-flop. In this design procedure, each cell in a Carnot map represents one of the present states in the counter sequence listed in table. From the J and K states in the transition table, a 1, 0 or X is entered into each present state cell on the maps depending on the transition of the Q output for a particular flip-flop. Step 5. Logic expressions for flip-flop inputs. The Carnot maps obtained help you to obtain the following expressions for the J and K inputs of each flip-flop. J0 is equal to Q2 into Q1 plus Q2 bar into Q1 bar and is equal to Q2 plus Q1 whole bar. K0 is equal to Q2 into Q1 bar plus Q2 bar into Q1 is equal to Q2 plus Q1. J1 is equal to Q2 bar into Q0. K1 is equal to Q2 into Q0. J2 is equal to Q1 into Q0 bar. K2 is equal to Q1 bar into Q0 bar. Counter implementation. The final step is to implement the combinational logic from the expression for the J and K inputs and connect the flip-flops to form the complete 3-bit gray code counter as shown in the figure. A summary of steps used in the design of this counter is given here. In general, these steps can be applied to any sequential circuit. First, specify the counter sequence and draw a state diagram. Then, derive a next state table from the state diagram. Then, develop a transition table showing the flip-flop inputs required for each transition. The transition table is always the same for a given type of flip-flop. Transfer the J and K states from the transition table to Carnot maps. And finally, implement the expressions with combinational logic and combine with the flip-flops to create the counter. So friends, that brings us to the end of our discussion in this lecture, and therefore we sum up. In this lecture, we learnt that a BCD decade counter exhibits a truncated binary sequence and goes from 0000 through the 1001 state rather than going from the 1001 state to the 1010 state. it recycles to the 0000 state. An up down counter is the one that is capable of progressing in either direction through a certain sequence. An up down counter, sometimes called a bidirectional counter, can have any specified sequence of states. A general sequential circuit consists of a combinational logic section and a memory section. So, that is it for today. See you in the next lecture with more on digital circuits. Thank you very much.